Hello everyone, welcome to tutorial 5 of the course Deep Learning for Natural Language Processing. So today we are going to cover transformers anatomy using Hugging Face. So this is adapted from the Hugging Face library notebooks itself. So I have connected my runtime to the GPU, as you can see. Now let's have some starter steps that you need to clone this GitHub, the Hugging Face notebooks, and do some setup of the notebook itself. So moving on, what is the transformers anatomy? As you might have seen from the lectures, so we have a input text which is tokenized. Let's say time flies like an arrow. Then we have the token encodings, which are then converted to token embeddings, which where we have positional embeddings added to them, which goes into the encoder stack, which produces some hidden representations for each token in the sentence. Then we have the query and the key matrices for the sentence, for each of the tokens in the sentence in the form of a matrix, which goes into the decoder stack for encoder decoder attention, and the query comes from the output, the ground truth, where the self attention cross self attention against takes place, the cross attention again takes place, and we have on top of it a classification head, which is used to predict the token predictions of the vocabulary, which gives the highest probability in the softmax, and which gives us the word given the given the input sentence. Now let's see step by step what each block is and code them up. So the encoder. So encoder is X in, it goes into a multi-head self attention. There are feed forward networks on top of each block. As you can see from the attention is all you need paper, which introduced self attention in the transformer and introduce the transformer architecture also. So as you can see, there are feed forward blocks on top of each multi-head attention block, and followed by some add and normalize layer normalization, which goes into, and we have an output representation, which is so you can see the encoder stack enlarged here. And next we have the self attention. Self attention basically is what fueling every LLM since 2017, the first paper when it came, attention is all you need, till now. So self attention is basically says that what is the word in my sentence that current word basically attends to. So as you can see, the flies more attends to source, and flies in self attention block. Here the insect, when time flies like an arrow. So here the self attention is source, and fruit flies like a banana, it's a insect. So just a pictorial representation of what self attention is. And let's see self attention in more visual way. So there is a library known as BirdViz, which helps which has many cool functions that you can play around with. Let's use the neuron view from the BERT model. So from transformers we are importing the auto tokenizer for tokenizing the BERT for auto tokenizer. Then from BirdViz neuron view import, we are importing the BERT model, and we are importing the show function from the BirdViz. And for the model we are using BERT base uncased. Let's call the tokenizer auto tokenizer from pretend, since the pretend model it's underneath calling the Hugging Face underneath, which is downloading, the weights are getting downloaded here. So let's run this, and from the model we are using BERT model from pretend using the checkpoint. So as I have already run this notebook previously, so it is not downloading, it is taking directly from the cache. Model, we are importing the BERT model from pre-trained using model checkpoint. Model checkpoint is the BERT base uncased, and as you can see, these are the attentions of each word to the other words, like CLS is more attending to CLS token itself and to AN, and there are also other tokens it is other tokens that it is attending to, but there is not much entropy or not much attention score to other words. So, let us say time is attending to more attending to arrow. Flies is also more attending to the arrow amongst all others. AN is more attending to the SEP token. So, if you also click on plus, it will show the query, the different keys and the query into key element wise, and then we have the softmax which gives us the highest prediction. As you can see, it gives us the highest, the arrow gives us has the highest softmax score. So, the time is most attending to arrow, as you can see from here also. Now, let us say flies, similarly for arrow, and so on and so forth. So, now what are these key, query and values? So, let us demystify them a bit. So, key, query, values are basically transformations of the input itself using query weight matrix, key weight matrix and value weight matrices, which are learnable. Then we have a matrix multiplication, which is then scaled. We have some masking, which is optional. Then we have a softmax, and then the matrix multiplication. So, q into k, the attention. So, let us see what each of these step by step. So, from transformers, again we are doing auto tokenizer. We need a tokenizer for the model, so that it can tokenize the text, and we are using model BERT based model. So, the text we are passing it like time flies like an arrow, we are tokenizing it. Now, in the tokenizer, so we pass the inputs to the tokenizer function, which takes in text, return tensors as PT and add special tokens as false. So, let us say the input IDs. So, input IDs are basically the auto tokenizer is converting the the text in the token, the words, into a specific index basically in the tensor. So, which is basically it containing 2051. So, time is 2051th position in the vocab, similarly the all others. So, it is the input IDs. So, the words are converting to input IDs, they are not yet embeddings. So, previously we have shown, so this tokenized text is getting converted into token encodings, which will then be converted into token embeddings. So, as you can see, the input IDs, so each word has been converted into token IDs. Now, from torch.nn and transformers autoconfig. So, what autoconfig is basically the configuration file. This is as you can see from the helper window itself, that is a generic configuration file that will be instantiated as one of the configuration classes of the library. So, this from transformers autoconfig, what it will do is it will take the configuration of the model that we pass in to the autoconfig from pre-trained function. So, we are passing in BERT base. So, all the configurations of the BERT base, like number of heads, number of layers, the embedding size, the key query matrix size will be in this matrix. So, now we are converting this input IDs, inputs.input IDs into an embedding. So, embedding, so is basic, so nn.embedding, which is basically the size, the embedding size is basically the vocab size by the hidden size. So, hidden size of each token that the BERT model accepts. So, by default BERT model has the hidden size of 768, and the vocabulary size of the BERT model is 30,522, and these are predefined by the model. So, nn.embedding is basically creating a simple lookup table that stores embeddings from fixed dictionary and size. So what it does, for each particular index we have an embedding, something like that. So as you can see, the token embedding is basically size of, this is the size of the token embedding. Now we have initialized the token embedding like this. Now let's fill this up with our input embeddings. So input embedding is equal to token embedding of inputs dot input IDs that we have from here for our case. Now let's see. As you can see, so let me print it out for you. So as you can see, the input embedding size is 1 cross 5 cross 768. This is due to the fact because we had 5 words. So here is 5 and this is one whole sentence. So 1 in the first dimension, 5 in the second dimension because it has 5 words, and 768 in the third dimension. This is due to the fact that each word is getting converted into a 768 8 sized tensor. So this is what, so the first row is what time, time corresponds to. This is the embedding of time, and so on and so forth for others. Now let's code up self attention. So as you already know that the the key, query and the value matrices are basically transformations of the input tokens itself. But here let us say for approximation we are approximating that input the key, query, value are same as input embeddings for the tutorial purposes, but actually these are matrices which are basically transformations of the input and they are learnable. And dimension q is key dot size, and then we do multiplication, matrix multiplication of query and key. As you can see from here, the equation, the attention score is basically softmax of q k transpose by root d k. D k is the dimension. So this is a scaled dot product attention, and then we have multiplication with v, the values. So BMM is basically bashed matrix multiplication, which, so torch dot BMM we put query and key dot transpose 1 comma 2, since we have to transpose. So along the first and the second dimension, and divided by the, see this is the scaling thing that we do, divided by square root of dimension k, we get a size of 1 cross 5 cross 5. So for the weights of q k transpose by root d, we need to do a softmax along dimension -1. So this is the last column, and so as you can see the sum, so these are the weights, and the sum across the dimension should be 1. So we are confirming that. Now attention outputs, these weights should be multiplied with the value matrix. So again we are doing this, and as you can see the attention scores are 1 comma 5 cross 768. Now let's put this thing into a function. So scaled dot product attention, query, key, value. So dimension k is equals to query dot size of -1. Scores are as similar to above, q into k divided by root d k, and weights is softmax of the scores, and we return the attention scores like this. Now this was single head attention, like what we have a single head. So as we can see from the paper, this is what we did right now. Now the transformer attention is all you need paper proposes at multi-head attention, like we can run. So multi-head attention consists of several attention layers running in parallel. Okay, so we have several attention heads. So this is one linear, this is another linear, this is another linear, linear transformations q k v, which is done into scale dot product attention, which is concatenated, and again some linear feed forward layer is there. Now let's put it in a class. So attention head. So this is the base class for so this is the attention head. So we so query is basically the nn dot linear of embedding dimension and head dimension. So this is, so what we, this what is the linear transformation that I was talking about for each of the tokens. So, for query key value we have a matrix, and linear is basically a matrix fully connected layer. This is basically it's doing the matrix of QKV, and these are learnable parameters as we will go. So, forward is basically scale dot put attention, we are calling this function scale dot put attention into the query the hidden state, and we are passing the hidden state to get the attention outputs. Now, let us write the multi-head attention. So, multi-head attention, so embedding dimension we are getting from the config dot hidden size, the number of heads we are getting from the number of attention heads we are getting from the config. So, head dimension is basically the embedding dimension divided by the number of heads. So, this is due to the fact that let us say 768. So, 768 is the hidden size and number of heads is 8. So, we will have 64 each embedding dimensions per head. 64 is the embedding dimension per head, which we then concat. For each head, to get the whole output, we concat the outputs from each head. So, self dot heads is nn dot module list, we get the attention head for each. So, attention head is embedding dimension comma head dimension for underscore the number of heads. For each number of head, we are initializing attention head, and output is basically a linear layer from embedding dimension to embedding dimension. And in the forward function of the multi-head attention class, we are concatenating the hidden state from each of the heads along the large dimension, and then we have the linear layer to get the multi-head attention outputs. So, let us do it from the config. As you can see, the attention output size is 1 cross 5 cross 168. Let us view it in Birdviz. So, again model is from auto model dot pretrain model checkpoint, output attentions is true, sentence A is time flies like an arrow, sentence B is like fruit flies like a banana. So, Viz inputs, we are tokenizer of sentence A, sentence B and return tensors. Attention is passed as this, sentence B start is along this. So, the SEP token is basically the start of B. And we again convert this into convert IDs to tokens, and we put a view here. So, convert IDs to tokens is what it does is that it converts those numbers in the dictionary to tokens itself for this so that we can see it here in Birdviz, and we pass these tokens in the head view. So, as you can see, let us in layer 0 CLS token has an attention to CLS and A of the second sentence, like has and most attention to SEP, arrow, flies and time, and so on and so forth. So, here we can also change the layers in the attention layer. As you can see, the attention layers are changed. So, each of the layer, so for each of the layer the capability of the model increases. So, let us say in the first layer it only represents able to catch the surface level information, then and so on and so forth. As the layer increases, the model tries to capture more intricate information from the text. That is why these LLMs are so powerful. Then we have the feed forward layer. So, from here, as you can see, for each multi-head attention we have a feed forward layer. So, feed forward layer is linear layer from hidden size to intermediate size, linear layer 1, then we have linear layer 2, then we have some kind of non-linearity. We are using GELU here, the transformer used GELU. I think most of you have heard about ReLU function. Then we have self dot dropout. Then we are doing linear 1, then we have GELU, then linear 2, then we have a dropout. So, feed forward is basically this feed forward config, which feed forward is taking the attention, the feed forward outputs is taking the attention outputs. From the attention outputs we get the feed forward outputs. So feed forward takes the attention outputs as inputs. As you can see, it has the size of 1,5,1768. Now, so here as you can see, we have a add a norm after multi-head block. So multi-head attention, we have a layer norm, then position wise FFN, the feed forward network, then we again have a layer norm. So this is known as post layer normalization. We can also have a pre-layer normalization where layer norm comes first, then multi-head attention, then layer norm, then feed forward networks. These are the design choices that the people that architects may make when designing a model. So the transformer encoder layer. So encoder layer, we have the layer norm 1, layer norm 2, multi-head attention, feed forward network. So for the transformer, we have a multi-head attention, 2 layer norms, and a feed forward network. So as you can see, we have apply layer normalization and then copy input to query key and value. So hidden state, then we have the self attention. So this is pre-normalization. So we are doing a normalization first, then the self attention, then we have a feed forward to, then which returns the scores. So encoder layer, so transformer encoder layer from the config inputs the input embeddings dot shape, and encoder layer we are passing it the input embeddings dot size. So it should produce after the encoder layer of the same size. So as you can see, the size of the tensor is same. Now we also know that in the embeddings, when the embeddings we add a positional component to the embeddings. So as you can see, so that it has some relative information when doing the self attention. It has some information as to which word should come after which word, because self attention, it's the relative position is not captured in the self attention equation, but if we can put this embedding in positional embedding in the embedding of a token itself, then it might be helpful for the self attention and for predicting the next words when we are doing a prediction from the decoder. So embeddings, so we have the token embeddings, then we have position embeddings, which are basically the matrices, then we have a layer norm, and then we have dropout. So sequence length is basically the create position IDs for the input sequence. So position IDs is torch.arrange. Arrange is the simple, as we have seen in tutorial 3. Arrange does this very beautifully. Then we are creating the token and position embeddings. So token embeddings is self dot token embeddings. So this is the token embedding. Then we create the position embeddings, and so the output embeddings is basically the addition of the token embeddings and the position embeddings. So both the position and the word is captured in the embeddings of a token, and then we do a layer norm and a dropout. So after we pass this to the embeddings layer, we see that we have the same size. Now the transformer encoder layer. So transformer embedding is from the embedding. So layers is basically module list of the. So in the transformer base, it has 6 encoder layers. So nx defines to number of how many blocks. So it had 6 and 12 and so on and so forth. So number of hidden layers, it had total blocks, it had 6. So the transformer layer encoder, we are the layers are basically the encoder blocks one after the another. We pass it to the embeddings. Embeddings is basically what this function is doing, this class is doing, and for each of the layers we are passing in the input of the output of the previous layer goes into the input of the next encoder layer. As we can see, input we are getting a size of 1 cross 5 cross 768 as the input. Now adding a classification head. Now let us add a classification head to the encoder. So we have a encoder, we have a dropout, we have the classifier. A classifier is what they, for let us say for a classification, it if it is a positive class or a negative class. So, we can get that information from the CLS token. So, CLS token is appended to every so CLS token is appended to in front of every sentence when we are passing it to the transformer. So, this CLS token basically captures what this sentence what is the intent, or if it is a classification problem, the whole sentence representation is present inside this one token, the CLS token, and we can use this CLS token for classification, for for what this sentence is a positive or negative, and so on and so forth. And so self dot encoder. So, here we are selecting the hidden state of the CLS token itself, then we are passing, and then we are doing a dropout, and we are training a linear layer which is a classifier, that what is the number of labels that we want to, what is the number of labels that we want our output number of labels. Let us say it is 2 by binary classification or a multi-level classification problem. We are so this classification layer will also be trained during the fine tuning of our transformer encoder, and we get output. Let us say we have the number of labels is 3. So, encoder classifier transformer for sequence classification, we pass in the config, and encoder classifier input IDs and size. So, as you can see, the encoder, after passing through the classifier layer, has an output size of 1 cos 3. So, for each token there will be 3 choices. So, for the for each sentence there will be 3 choices. Now, let us see what the decoder is. So, decoder similar, but here in the decoder we have a encoder decoder attention in between, with the KV comes from the encoder, and the X input, the Q, the query, comes from the decoder, and then we have the encoder decoder attention, and then similarly from the encoder we have the classification head and the token predictions, and so on. So, let us say the sequence length was like this, then we, so for the decoder to predict the next word, it should not see what what the next word is, because the key and the, so in this the X input consists the next word, the ground truth is going into the decoder, but during encoder decoder attention it should not see what is the next word. Otherwise that makes no sense. The transformer is going to predict the next word, but it should not see what the next word is in the ground truth. So, what we need some kind of masking. So, as you can see in the mask, we do a trill function which gives. So, if you want to know about trill function, you can just search torch.trill and you get a good documentation about it. So, here we get a triangular matrix, as you can see along the main diagonal, and we are mask setting the others to zeros. So, for the first position it will see only the first word in the ground truth. For the second position it will see the first and the second. For third and so for the first position it only sees the first word and will not be able to see the rest of the words in the ground truth, because it has to predict the second word. So, and we are setting the scores of masked field to -infinity, so that it will not be taken up in the softmax equation. So, we are predicting this, then we are predicting this, then we are predicting this. So, scores, so this is the mask, and scores we had previously the scores. So, we are masking and filling. So, masked fill, we are putting it mask equal to 0. So, where there is 0 we are putting it to -infinity. Now, what we are doing is basically we are doing a scaled dot product attention similar to before. So, if mask is not none, we are putting it to a -infinity. This is the scaled dot product attention in the encoder decoder attention, which basically says that if mask is not none, and then scores are, we are filling it to -infinity, so that the model encoder decoder attention is not able to capture what is the next token in the ground truth, and it will predict that token instead. And similarly, it will give the encoder decoder attention values from the weights. So weights is basically softmax of these scores, and there we get the attention scores from the equation itself, k query transpose into V here. So yeah, that's all for today. This is the transformer tree of life. Meet the transformers. So encoder decoder, we have encoder level transformers like Distelbert, BERT, Roberta, XLM, XLMR, Albert, Electra, DBERTA, and for the decoder level, decoder level transformer, we have GPT, GPT-2, GPT-3, GPT Neo, GPT-J. We have now chat gpt, all these llms, this llama, mistral, these are all decoder level llms. Then we have encoder decoder models like T5, BART, M2M, Big Bird, and so on and so forth. So yeah, that's all for today, and I hope you got a brief introduction to the Hugging Face library. And please go through the library itself. It has a nice documentation, and thank you. That's all for today.